Hi, everybody. This time we're going to talk about how you actually create the formulas for ionically bonded compounds. Now, nature makes these all by itself, and our goal by the end of this is to be able to take any non-metal main group element and any metal main group element and predict the formula of the compound that nature is going to produce. Now, metals, as you remember, tend to produce positive ions. Non-metals tend to produce negative ions. And when nature throws these compounds together, it makes compounds that have zero net charge. So let's take a look at how this works. If you are going to chemically react magnesium and oxygen. Now, magnesium is a group 2 metal, and it tends to produce ions that are positive 2. If you remember from our last chat together, I had you put the most common ion produced at the top of every one of these tall main group families, and magnesium is +2. Oxygen from group 16 tends to make -2. So if you wanted to make a compound out of magnesium and oxygen with a zero net charge, how many magnesiums and how many oxygens would you need? Well, if you burn magnesium in oxygen, what nature is going to do is take one of each, and you would end up with magnesium oxide, one magnesium and one oxygen, because +2, -2 would equal 0. So let's do another one. Let's say you were going to bond magnesium and bromine. Well, magnesium we just worked with has a charge, most common ion of +2. Bromine is a halogen. Most common ion of the halogens is -1. And if you were going to chemically react those two, the goal, of course, is to have a net charge of the compound of 0. And so how many bromines would you need? You'd need 2 bromines to react with the magnesium. And how we write this in chemistry is 1 magnesium and 2 bromines. We write that with a subscript. The subscript would indicate 2 bromines. And that's how we'd write that one. Potassium and oxygen. Potassium is a group 1, and those produce ions of +1, so potassium +1. Oxygen -2 from right there. That's the most common ion. Again, the total charge we want is 0. So how are we going to achieve that? Well, we would need 2 potassiums +1 oxygen. So we'd have +2 and -2, and we would end up with a total of 0. And we would write it 2 potassiums, 1 oxygens. And we never, ever, never, if you recall, never write subscripts of 1 down below. The element symbol all by itself indicates 1 atom. We only write subscripts to indicate more than 1. Now, what we've been doing is logicking this through, doing a little bit of math, and that's wonderful and that works, and we are mentally trying to figure out what nature's doing. But here is a set of steps to help you do this a little bit faster. Now, these are some steps to ionic bonding. I want you to put a star by this in your notes. And these are the steps you and I are going to follow. And I like following these steps because it's a little bit faster technique. So the first thing we do is find the most common ion of each element we're working with. Always write the positive ion first. Ask ourselves the question, are the digits or the numbers the same? If the answer is yes, we have one of each. If no, we crisscross. Then we ask ourselves, is there a common denominator? And then lastly, we use parentheses with multiple polyatomics. So these are the steps we're going to follow, and let's go through some examples. So for beryllium, step 1, find the common ion of each. So for beryllium, beryllium is right here. It's a group 2 element. Most common ion is +2. Sulfur is right there. It's group 16. Most common ion is -2. So we did this, found the most common ion. Write the positive ion first. And the positive ion is written before the negative one. Why is that a big deal? Well, when you write your name, you always write your first name and then your last name on a legal document. That's how it is done. In chemistry, we write the positive ion followed by the negative ion. When we name an ionic compound or write an ionic compound, that is how it is done. So that's why we have to have the positive one written first. Then we ask ourselves the question, are the digits the same? Meaning, is this a 2 and that's a 2? Well, the answer is yes, they are. Our goal is, nature's goal is to come up with a total charge of 0. So 2 plus positive 2, negative 2. So what do we have? One of these, and the compound is going to be BeS. Pretty simple. Okay, let's do another. Chlorine. Most common ion is, this is from the halogens, its most common ion is -1, and strontium is from group 2, most common ion is +2. Write the positive ion first. Well, it's not, so please don't be a lazy pants. Take the moment, take the few seconds it took to rearrange these. Rewrite them with the positive one written first. Just takes a second, and if you don't do this, you will get them wrong. Write the positive one first. Then you ask yourself the questions, are they the same? No, they're not. This is a 2, this is a 1. So then we go to this option, crisscross. This crisscrosses down there, this crisscrosses down there. And so SR, the 1 comes down, but we never, ever, ever write a subscript of 1. Never, ever do it, because strontium, the symbol, represents 1 atom. Then the 2 crisscrosses down there, chlorine, 2, and we never, ever, ever put a plus or a minus in the subscripts. So it's SrCl2. Okay, let's go through a few more. Calcium and phosphorus. Calcium, common ion is +2. Phosphorus is from group 15. Most common ion is -3. Is the positive one written first? Yes. Negative second. Are they the same? No. So then you crisscross. This goes here, that goes there. It's kind of like a little disco dance. So Ca, the 3 comes down. Never write charges down below. P, the phosphorus, the 2 comes over, and that's my compound, Ca3P2. The next one, sulfur and tin. Sulfur's most common ion is -2. Tin's most common ion is, it is in group, tin's right there, it's in group 4. And remember, when I asked you to write the most common ion number at the top of the charts, I said for group 14, plus or minus 4. The reason being, it depends on if it's a metal or a non-metal. Metals tend to produce positive ions. Non-metals make negative ions. Well, tin is a metal, so this is going to be +4. Is the positive metal written first? No, it's not. If not, rearrange it. Sn +4, S -2. Are they the same? No, they're not. Crisscross. This goes here, this goes there. Sn2, S4. Are we done? No, we're not, because there's one more step that we have been ignoring because we haven't needed it till right now. This one, is there a common denominator? All right, here's the situation we're talking about. This crisscrossing, ladies and gentlemen, is just a trick. It is a fast way of ionically bonding. But our goal, the ultimate goal, is to predict what nature is going to do. And what nature is going to do is come up with a simple package with a net charge of 0. And we want to predict that. So if you end up with a compound like this, and you have a 2 and you have a 4, that should ring a little alarm bell in your beautiful little brain. I'm trying to draw a bell. A little bell should go off in your brain, and you should say, uh-oh, that's not right, because nature's going to make the simplest absolute compound it can. And if this number and this number, you can have a common denominator, you can divide them both by something, then do. Both of these can be divisible by, I'm going to change colors, both of these are divisible by 2. And so what nature's going to produce here is SN. If you divide 2 by 2, it's 1. Never write 1 as a subscript. And sulfur, 4 divided by 2 is 2. This is the compound that will be produced for this situation. You only use this step if you end up with subscripts like a 2 and a 4, or a 3 and a 6, or a 4 and an 8, which you're probably not going to have, and only when ionic bonding. Okay, here's what I'd like to have you do. Hit pause and try these. Now, and then we're going to come back and I'm going to go through them at warp speed. Now, please, please try these and then let us go through them together, because this is how you learn how to do stuff. Not just watching me do it, but doing it on your own. Yes, making some mistakes, fixing the mistakes, and then getting better. So give it a go, and then we'll come back and go through them together. All right, here we go. Lithium. Whoops, iodine is a -1. Lithium is a +1. Is the metal first? No, so rewrite it. You have one of each, and the compound is Li, big I, lithium oxide. Next one, nitrogen is -3. Sodium is +1. Is the metal first? Nope, rewrite it. Na, -3. They're not the same, so crisscross. This goes there, this goes there. Na3N, 1 comes down. Do you ever write 1s in subscripts? No, never write 1s as a subscript. Na3N. Magnesium, +2. Where's the 2 come from? That's the most common ion produced by that group. Phosphorus, -3. That's the most common ion produced by that group. Oop, that's supposed to be a 2. Are they the same? No, crisscross. This goes there, that goes there. Mg3p2. Hydrogen. Hydrogen's a group 1, so it's going to be +1. Oxygen's group 16. Most common ion there is -2. The positive is written first, crisscross. H, the 2 comes over. Notice no plus or minuses. The O, the 1 comes over. And do we write 1s as subscripts? Never, ever, ever. And hey, hot diggity, we just made water, H2O. All right, you will have lots of practice doing this on this week's study guide. This is a skill you're going to be quizzed on for this week's quiz. And as the course continues, when we start writing chemical reactions and things, you're going to have to know how to do this. So this is not a one and done. You're never going to see this after this week. So please take the time and learn how to do it. See you later. Bye-bye.